So demonstrations don't get much more simpler than this as far as required apparatus, right? This is just a little 6-volt permanent magnet DC motor, and a little device here, guys, right? And have a power supply. And wow, you know, it's a revelation that if I crank up the voltage on it, we get rotation out of it a little more. So there's 6 volts. There's the current. Well, what's new about that? Absolutely nothing, right? So most of you guys will be aware that if I increase the load on the motor here, keep an eye on the current, and you'll see the current goes up, of course, as the load increases on the motor. Again, nothing really new there, guys, right? The point to the video is, guys, is that motors are, you know, basically magnetic fields and coils of wire that cut the magnetic fields, and the electrical power is converted into rotation, right? You know, by the opposing fields, without getting too deep into that. So basically, you have a magnetic field, the coils of wire, and movement, cutting the flux, right? Well, but that sounds a lot like a generator as well, right? Essentially doing the same thing, only converting the mechanical input, the rotation, into electrical output, right? So the point of the video, realize that when a motor's in operation, it's also acting as a generator. Let's slowly crank the voltage up here and see what effect it actually has, right? So again, let's quickly go to 6 volts just to remember the actual figures. Let's call it 0.2 amps, you know, keep the math simple. Right, at 6 volts. So if we were to take a meter, and we'll do that momentarily, we could measure the coil's resistance here, and would be able to figure out how much current it should draw, right? If we apply 6 volts at a particular resistance, Ohm's law tells us it will draw X amount of current without doing the math, right? We don't know the math yet because we don't know the resistance. Although we could work it backwards, I suppose, from what we've seen here. But perhaps these figures are not actually telling us the whole truth. Right, let's slowly ramp up the voltage here. Let's ramp it up quick enough that you can see we've got some rotation here, right? When does it start to rotate? It's a 6-volt motor, guys, 6-volt DC motor. And of course, to get it rotating is going to take a wee bit more voltage. You have to overcome the inertia, of course, of the motor itself. So I don't know, let's call it maybe 0.6 volts. Look at the current there. Weirdly, not that much less than at 6 volts, right? So that doesn't really seem to add up. What's the story with the mathematics there? In fact, it makes sense. If we apply less voltage, then the current should go down, right? What's going on here? Less voltage and the current is going up. Apply a wee bit more voltage. That doesn't make a whole lot of sense, does it? At 1 volt, why is there way more current at 1 volt than there is at 6 volts? Again, that doesn't make a whole lot of sense. See if we can just hit the sweet spot here. No, keep in mind there's no rotation, guys. Anytime there's voltage and amperage applied, there's power being applied. Power has to do work. So if there's no rotation, this is translating into heat, right? I can feel a wee bit of mild heat there, not a great deal. I don't want to burn out the motor. So there's 0.3 amps at just over a volt. 300 milliamps at just over a volt. And yet at 6 volts, 200 milliamps? What's the story? let's measure the resistance of the coils here, see if we can make any sense of the mathematics, and then we'll get a wee bit more tooling involved and see if we can make sense of what's happening here. Why am I demonstrating this? See the battery there? That battery's state of charge took the starter out in this car. Partially to do with the state of charge in the battery, partially to do with mass stupidity. How can a low charge battery, a low state of charge battery, cook a starter? How does that make any sense? If the battery's dead, how can you end up burning out a starter? How does that make any sense? Now keep in mind, guys, it's no great loss to me. I'm actually parting this car out, as you can see. There's 3 other SX4s in the driveway there. This one was heading for the graveyard, but I did want to be able to move it out in and out my garage here while I was stripping it. Okay, so you can see here, guys, I've got my Modus actually hooked up here, and I've got the display on the telly so you can see things a bit clearer. So right now I've got the leads and open circuit configuration here, as you can see. In fact, so you can see there's no trickery, let me just short the leads together. They're going to the meter. And you can see it's a dead short, right? Okay, 0 ohms. Let me open it up again, just to open the and rover scale. Right, let me go across the motor here. Let's check what the coil actually reads. Take a second. About 8.5 ohms for the resistance. So we're just reading through the coil here, guys. This is the meter's just in parallel with the power supply. Power supply is disconnected, of course. So we're just reading the coil on the motor. Okay, so what was that? 8.5 ohms. So Ohm's law tells us that if we apply 8.5 volts, this is only a 6-volt motor, guys, but I think we can stress test it here to make a point. So would it make sense if I apply 8.5 volts to 8.5 ohms, we should have 1 amp of current, right? If things are that simple, let's try it. Okay, there's exceeded the rated 6 volts already. So again, just to keep the math as simple as we possibly can, 8.5 volts across 8.5 ohms. Yeah, that's not, no, that's no cricket, is it? Something's amiss here. We're not getting the whole story here. So if this was 8.5 ohms of resistance, apply 8.5 volts, we should have 1 amp. That's as simple as I can make the math, guys, right? 8.5 divided by 8.5, 1 amp. And yet clearly we were only getting 200 milliamps. Okay, right, so there must be something else to this. Getting back to what I was saying about a motor acting as a generator. So if that's true, if we apply 8.5 volts and we actually put a scope onto the leads, well, what we're going to see, let's see what we see. So I'm going to apply back to the 6 volts, okay, on the power supply, and I'll take you back so you can see that I'm not talking any shit. Why would I? It would completely undermine the point of the demonstration, right? So you can hear the motor running, I think. So keep an eye on the, you can see on the scope here. If you look in the upper left hand corner there, it shows you the actual voltage, average voltage, DC voltage that's being applied. And okay, so 6 volts, all we can really see is the terminal voltage that's applied to the motor with a straight DC power supply, right?
Okay, so where's this voltage I'm talking about? Like, how the hell can we see this? When this motor is spinning, guys, it is acting as a generator. You have a permanent magnet and you have coils of wire spinning inside this housing. That is the definition of a generator, pretty much, right? So how do we get to see this voltage? The trouble with this is, all this is going to show us is the terminal voltage, which is applied to the motor itself here, right? You can see we can't see anything else. Is there any other way we can approach this? Yeah, I think so. So what I've done here, guys, it's the same setup, but from the power supply, the DC power supply, I've introduced a pulse width modulation or duty cycle controller in line before the power makes its way to the motor. Now this is usually done for speed control purposes, but in this instance that's not the case. It will become apparent why I've introduced this in just a moment, because I want to introduce some gaps into the signal here. For a reason, again, it'll become apparent in a moment. Okay, so without getting into the long drawn out story about what pulse width modulation or duty cycle control is all about, what I can effectively do is through this controller here, it effectively chops the signal, the DC supply in this case, which is being applied, the power which is being applied to the motor. So does it make sense that at 100% duty cycle, that will be 6 volts effectively, right? There we go, turn it on. You can see I'm on here, the power is out and the motor is spinning. You can see we have a straight line again. My leads are set up here for the scope that we're just going across the terminal of the motor essentially. So what we're going to see is again that same terminal voltage that is applied, right? But we couldn't see any counter electromotive force or back EMF on the line, because all we're going to see is the applied voltage. So as I was saying, motors effectively act as generators, guys, at the same time, and they generate what's called counter electromotive force or back EMF. You might have heard that term, but we couldn't see it without the introduction of this controller here, because we just have a steady state DC being applied. We can't see any effect, right? But we can with the controller here now. So let's turn it on. Keep an eye on the voltage on the left hand, upper left hand corner there. So what I'm going to do is I'm going to step down from 100% duty cycle. You'll hear the motor speed dropping to 80%. So what we have here is effectively a square wave being applied. It's 80% on, 20% off. We seem to have this little artifact here on the trace. What's that all about? You'll notice also that the effective voltage, the average voltage which is being applied, is dropped significantly as well. Let's go down to 50% here. As you would expect, because we're dropping the applied voltage effectively, the speed of the motor is going to slow down as well, right? Okay. So now what we have here is at 50% duty cycle, it's off for 50% and then on for 50%. But yet, again, we're seeing this, right? What's this all about? Let's just slow the speed down, you'll hear it. I can't get everything in frame at the same time here, guys. Can you see that the duty cycle is dropping? Something else is dropping as well here. Look at the amplitude, if you will. Not really amplitude, it's not really a AC signal, but look at the voltage, the effective height of this line here. Keep an eye. Relative to the top of the pulse. You see how that's creeping up as the speed increases? Okay, so let's go 100% again, just to make the point. That is effectively the same as without having a controller in line, because it's 100% duty cycle, yeah? You'll see I've no manipulated anything, guys. All the settings are still the same. So what this is allowing us to do is actually see a gap in the applied voltage, right? And that gap in the applied voltage is allowing us to see the voltage, the counter electromotive force, or back EMF, that the motor is actually generating right here. And you'll notice that with an increase in speed, like any generator, with an increase in speed, the coils are cutting the magnetic flux that much quicker, is generating more voltage. Now, it's never going to exceed the line voltage that's applied. Even if we go up to 99% here, you'll see there's still a significant gap. Can you see that? When it does appear, it's difficult to see because the gap is so small. Let's go something reasonable so you can see maybe 80%. You can see there's still an effective gap between the counter EMF and the applied EMF voltage, if you will. Again, let's go to 50%. Right. Okay, so let's just hold that image there. I can turn this off so we don't need to have the annoying buzz in the background here. Okay, so this is the applied voltage. This is the back EMF, or counter EMF. So what's actually operating the motor with respect to rotating it? That would be effectively the difference, or the differential between the two. That makes a lot more sense why we only had 0.2 amps with a it was an 8.5 ohm resistance with the coils, right? With 8.5 volts applied, we should have seen that. We should have seen 1 full amp of current. But if it's rotating at speed of 8 volts and the motor is generating a counter EMF of X amount of volts, what we're only actually seeing is current being applied from just the differential voltage. That makes a lot more sense, right? Again, don't you beat the point, guys. The motor also acts as a generator, and by using a duty cycle controller, pulse width modulation, if you will, two sides of the same coin, we can introduce a gap into that applied voltage that allows us to see in that space of time the counter EMF. Okay, now if you accept this to be the truth, and I do, who are you going to believe, me or your own eyes? Let's get back to the story with my battery and my starter that burned out. How is it any different? How is the starter in my car any different from the battery, power supply in this case, or the motor here? We've seen for ourselves that if we have an applied voltage and we slow the rotation, we've seen that at the beginning of the video, the current actually goes up, right? Now, if the applied voltage drops to the point where the rotational speed of the motor drops, we also seen that the current goes up. But couldn't you really rationalize why? Can you rationalize why now? Because when the applied voltage is high, if the rotational speed is low, the counter EMF is very low. Now, as I said before, the scenario was a dead battery, guys, right? Well, these things are rarely ever truly dead. They're still putting out a pretty significant voltage. Yeah, you can't really tell. The car had been sitting for 3 months. Clearly, that the engine's quite bound. There's been no oil rotating. All of the accessories are pretty stiff. I could tell by the rust on the serpentine belt, and it was struggling to rotate, loading up the starter even more. So with a partially discharged battery, significantly discharged, the starter can rotate so slowly that it's not really generating any counter EMF. Because it's not generating any counter EMF, even a battery with a relatively low capacity can generate enough current that it can cook the wiring, the heavy gauge wiring, and it can cook the starter itself internally. There's a little braided line from the solenoid to the starter. In this case, it was cooked. It was corroded, it was old, but it finally gave up the ghost in that scenario where the rotational speed was very low. Again, what difference does that make? When the rotational speed is very low, the counter EMF being generated is going to be very low. It's basic physics, right? Rotational speed affects the amount of voltage in a generator, but a motor can act as a generator, and we've seen it here for ourselves. I hope this makes some sense, guys. It's just a shame that the scenario rarely presents itself where you have a motor that's rotating that slowly and you think, oh, the battery's dead. And despite the fact that I know this, I continued to hold the key with an extremely slow rotation, eventually cooked the starter, even with a virtually dead battery. Right, that's it, boys. I hope this makes some sense. Cheers. I don't believe it. Let me rotate the motor mechanically here, turning the motor into a generator, and see what we get on the scope with respect to the trace. I've got the trigger set up to hold the image when the rotation stops.